Okay, moving into chapter 2, which is dealing with differentiation, we're going to start with section 2.1, which is the derivative and the tangent line problem. And in this section, what we should be able to do is find the slope of a tangent line for a function. Number 2, use the limit definition to find the derivative. And number 3, understand the relationship between differentiability and continuity. Okay, you've heard of tangent lines before, and you've used tangent lines, and more specifically in geometry. But in geometry, it was more specific to a tangent to a circle. And you know that when it was tangent, they basically just had one point in common. And that was basically what you were looking at. And there's different formulas and theorems and different things you can do to find lengths and so on. Again, you could easily find the slope of the tangent line if you knew what the radius was. And you could find the 2 points from the radius from the center and the point on the circle. Once you knew the slope for this side, then of course, because this was perpendicular here, you would know that the slope would be the negative reciprocal for it. And so you basically just focused in on that idea. When we get into the calc, we're going to look at the tangent lines a little bit differently. And what we're going to be looking at in calc are tangents to curves, not necessarily circles here. So we're going to look for tangents at different specific points on a particular curve. And just giving you some examples here where they would be tangent. Oops, just pretend it's tangent there. But you can see that a curve, this particular curve, could have an infinite amount of tangents as you go along its curve here. And what we're going to do is we're going to find what the slopes of these are and what the equations of these lines are going to be. So you can see it's going to get a little bit more difficult. And to lead you into what we're going to be doing, here, for example, is f of x is equal to x squared, and I've kind of drawn the parabola in there. And what we're trying to do is we're trying to find the slope of this tangent line at this particular point. Okay, when you're finding slopes, you already know that there is a slope formula, y2 minus y1 over x2 minus x1. But this formula requires 2 points. And how do I find the slope if I only have 1 point to work with? And that's where the big issue comes into play with this. Well, you can already tell that what we're going to do is we're going to use 2 points. Okay, so I'm going to take the point that I do know, 1, 1, for example, and this other point up here, 2, 4. And what I'm going to do is I'm going to use a secant line. And a secant line is just a line that kind of goes through 2 points on that graph. So I do have 2 points. The points happen to be 1, 1, and 2, 4. And what I'm going to do is I'm going to find the slope for that. And most of you already know how to handle this. Shouldn't be any issues. We get 3 over 1, or the slope is 3. But you can see that the slope of this line is bigger than the slope of this line. So then what can I do to get a more accurate idea of what the slope is for this line? Well, I think you guessed it. What we're going to do is we're going to choose a point that's just a little bit closer to our initial point down here. And so what I'm going to choose is a point just a little bit closer to it. Let's say 1.5. So halfway between the 1 and the 2. And if I do plug in 1.5, I'm going to get a y value of 2.25. And so what I can do then is just go ahead and find the slope. Once again, pretty simple to get through this. 1.5 minus 1, which gives me 1.25 over 0.5, which gives me a slope of 2.5 now. Well, 2.5, you can see, is still a little bit bigger than this line. So what we want to do is get a little more accurate a reading. So what I'm going to do is I'm going to choose a point that's even closer to it. And an option that I have to get even closer to that is to use, how about 1.1? And if I choose 1.1, my y value would be 1.21. And if I go ahead and calculate the slope on this, what you're going to see is that I'm going to get a little bit more accurate a reading. And in fact, in this particular case, it comes out to be 2.1. And that's a little bit better because you can see that 2.1 would be just, 1.1 would be just outside of this 1. It's going to be pretty close to what this red line will look like, but it's still not exactly there. So what else can I do? Well, why not get even closer? So if I do have my initial point of 1.1, what if I chose 1.001? That is so close that there's not a whole lot of room in between the two. And you can see the y value is there. When I go ahead and I calculate this, this is going to give me this value, which comes out to be 2.001. So I've used 3 successive points here that are getting closer and closer to the target point that I want, which is 1, 1, so that I can find out the slope of this tangent line. I started with 3, got to 2, 5, 2, 1, and you can see that the closer and closer I get, this is getting closer and closer to the number 2. And that's really what we're going to be looking at here. What we're really doing is, of course, finding a limit for this. And what we're going to do is we're going to find the limit as we approach our particular point here. Okay? But let's go ahead and develop that idea before we get into that part. To develop this idea, what I'm going to do is I'm going to generalize it a little bit more, and I'm going to take some random point x on the number line. And I know that x is going to give me a value of f of x. I'm going to plug in x into the function and find my value. And what I'm going to do then is I'm just going to pick a random length here of delta x. And if that random length happens to be delta x, then this point out here has to be x plus delta x. And then that means its y value is f of x plus delta x. And what were we doing for finding the slope? What we were really doing was using the slope formula for this. So if I take f of x plus delta x minus f of x all over delta x, that would be my slope. And then what do? We found the point that was closer, found the point that was closer. Really what's happening is this delta x is approaching 0. So really to find the slope, what we were doing was making this delta x get closer and closer and closer to 0. And as we do that, this should look familiar. You were working on some of those problems in the previous chapter, going through some of those limit problems. It's really a limit problem, but it's the definition of a tangent line with slope m. And we will use this to find the slope of a tangent line at any point C. So let me go ahead and show you an example how this is going to work. Okay, in this example, what we're asked to do is find the slope of the tangent line to the graph of f of x equal to x squared minus 2 at the point negative 3, 7. And what we're going to do is we're going to use the definition for that slope. And that definition happens to be this limit problem right here. So we go ahead, we're going to use this. And the way we're going to use this is as follows. All right, what we're going to do is we're basically going to take this expression, substitute it into our function, and then subtract the function that we're dealing with. And then we're going to algebraically manipulate this, simplify and all that fun stuff, and eventually come up with an equation that will help us to find slopes of tangent lines to a particular curve. Okay, so this is what we're going to end up doing. Again, we're going to substitute this into that location there. So this is going to be x plus delta x squared minus 2. I take that x plus delta x, substitute it into my function. Then I'm going to substitute my function from that. And that's all going to be over delta x. Now the rest of this, you're done with the calc step. Now it's just a matter of doing the algebra. And all we're doing with the algebra is expanding this out. So if I take x plus delta x squared, I will get x squared plus 2x delta x plus delta x squared minus 2 minus x squared plus 2 over delta x. And what you should notice is the terms without a delta x should cancel out. And what's left are terms that have delta x. Well, since they all have delta x, what I'm going to do is I'm going to factor that delta x out. And when I factor it out, this is what I end up with. And lucky for me, the delta x's cancel out. And so what I'm going to be left with is this expression here. And for this expression, once I apply the calculus concept once again, as delta x approaches 0, that means this becomes 0. I end up with this equation. And what we're saying is that this equation here is what we can use to find the slope at any particular point along this curve. And since we have the point negative 3, 7, in order to find the slope at that location, all I need to do is substitute my x coordinate into it. And what I find is that my slope comes out to be negative 6. Okay? Now, because we've already gone through all the work here, I can easily find the point at any other location. So if I wanted to, let's say there's a part B to this, find the slope of the tangent line at the point 1, negative 1, it would just be a matter of substituting 1 now into that equation. And I would see that the slope at when x is equal to 1, the slope comes out to be 2. And I can keep doing that for all kinds of different points. But the initial work is right here. Now I want you to pay attention to one thing. Notice that every single line, whenever I have equals, has limit delta x equal to 0. You have to have this specified. They do not like when students do something like this. Oh, this is all the same, so I'm going to do that. They really, really frown upon that. So you've got to refrain from taking a shortcut and doing it that way. You have to list this out. Yes, I know it's going to seem tedious. Yes, I know that, oh, why is this? Do I have to do all this? It's not me, it's them. They want, when you work something out like this, they want to see proper calculus. They want to see that this limit is equal to this limit, equal to this limit, equal to, which is true. That's proper mathematics. If you leave this off, are these two equations or two things equal to each other? No. This is a limit and this is just some expression. They want to make sure that it is proper mathematics for it. So you kind of have to go through that process there. Okay, so don't take shortcuts. Write it all out. At the end, it's going to pay off. So once again, as we go through this process, you can see that it gives us some equation, and that equation is what we're going to use to find the slope of tangent lines at any particular point. Well, this particular process does also have a name to it, and that happens to be the definition of the derivative of a function. And instead of writing it as slope equals, what we are actually going to do is write it using this particular symbolism. And that symbolism, of course, is referring to the derivative. So we still have this other piece out here, which is the slope part of it and how we're working with it. But what we're going to add is this piece here in front. It is f prime of x. So maybe my handwriting isn't as neat, but it should have a little tick mark up here. And whenever you see this tick mark up here, that is going to be known as the derivative. Okay? So we're looking at the definition of the derivative here. And this is a long way of finding the derivatives, but it's something that you have to know, you have to be able to use, because there are some times where there is no algorithm to find the derivative of a limit. And what you have to do is you have to fall back to this concept here. And I'll show you on some problems as we get further along when we get into trigs and so on, how you can't just use an algorithm to come up with the answer. You need to be able to use this. Eventually you'll memorize the process for it, but at least you'll know what to do with that one. Okay? Now, there's different ways to write the derivative, and I've shown you one here that, of course, is f prime of x. Let me write that a little bit neater. F prime of x. There are other ways to write this, and what you're going to see often is dy over dx, and really what it's referring to is the derivative of our function y with respect to x. Of course, assuming it's written as y equals. If it's written as an f of x equals, then of course you're going to see f of x. But if you see y and you want to find the derivative, more than likely they will write it dy dx. You can see y prime, and that is a shorter version of this. So y prime is okay to write with that, but most of the time you'll see everything with the AP and the College Board, they will write it this way or this way. There are other formats that we can use. We can find the derivative with respect to x for some expression or some function, and one that's not used a lot, but there are some books that have it, is written this way. And they're all really different ways of expressing the derivative. And the derivative, again, is just this idea, this limit process up here. All right, I'm going to stop the first video here before I get into examples of what to go through, because I've already defined the derivative here. The next video will pick up with more examples to work on.